Hello, welcome back to our series on errors and power, which is taken from chapter 15 of the A-level statistics syllabus. Quick reminder of the definitions. A type 1 error is rejecting H0 when H0 is actually true. A type 2 error is accepting H0 when H0 is false. And if you correctly reject H0 when it is false, that's referred to as the power of the test. Alternatively, if you have worked out your type 2 error because the conclusions are complements to each other, if you are rejecting H0 when H0 is false, that's the opposite probability to accepting H0 when H0 is false. So if you've worked out your type 2 error, you can simply take that away from 1 to work out the power of the test. So in the recent 2 videos, I've gone through some normal examples. I've also done 2 exam questions of normals. Unfortunately, they're the only errors and powers exam questions we've had so far. Which were taken from the sample material paper and the 2019 series, which is the only legitimate series of students sitting external exams. We have had the 2020 October resit, but nationwide that was quite a low sample size, so probably not worth discussing as to the legitimacy or the validity of the usefulness of those resources. So, what I want to cover in this video are how we go about things differently for a binomial test. The tricky technique of a type 2 error is actually simplified because we're talking about a discrete number line. We're not talking about a sample mean distribution like we're doing in a normal test. So we don't have the complicated component of remembering sigma over root n or any sort of tricky algebra. So type 2 errors are simplified for binomial. We need to think about our number line. We need to think about calculating the probabilities correctly. But the type 1 is actually just that little bit trickier to remember. It's no longer just the significance level, because we very rarely will be able to achieve the actual significance level to be the significance level set in the question. Here's our first example. It's a one-tailed left, because we're testing for less than 30%. And if we set up the model, so binomial with number of trials 25, let's assume H0 is true for now. Let's carry out a critical region for this test. So how would we go about that? We're looking for were the decision changes between accepting H0 and rejecting H0. If you don't know where to start, you can work out the mean. The mean here, 30% of 25 would be 7.5. So because I'm testing for less than 30%, 7 would be an okay starting point, but the probability would be too big. So 6 is a better starting point, maybe 5, and maybe 4. All right. You do have this technique on the calculator of inverse binomial. So if I set the calculator on play, if I do a distribution binomial, inverse binomial, I've got a nice little starting point. So sample size 25, assuming 30% proportion. And I'm aiming for a 10% significance level rather than the usual 5%. Sometimes it'll give a warning. And here it has, it's given a warning. It said 5 or 0. So 5 is a good starting point. So let's work out less than 5, less than or equal to 5. Fortunately, with this being the old style calculator, it doesn't have a lower option, so x in this situation is the upper of 5. So 0 and 0 is a lower, 5 is an upper. on the new calculators, which I'm hoping you've got, still generates this 0.193 BCD probability, which is too big. It's bigger than 10%, so 5 is actually in the acceptance region. So we're going to have to lower that to 4, less than or equal to 4. So 0 to 4 generates a 0.0905, which is less than 10%. And it is 10% because it's a one-tail 10%. We don't need to half that to 5. Good. So that's a rejection. So 4 or less is when we start rejecting. So that is our critical region. Now, the probability of a type 1 error is the probability of rejecting H0 when H0 is true, which is what we just worked out. It's the probability of your critical region. Now, in a normal, you can actually genuinely achieve an area of 5% or 10%, whatever you desire. But the probability associated with this discrete number line is just smaller than the significance level. Right, and you'll notice I'm changing the probability here. So the definition of type 2 is the acceptance region. So let's draw a number line out, and the 4 and 5 is where the changeover occurred. On the calculator, unfortunately, I'm having to talk about what my type 2 is and what my power is, etc. Maybe pay attention to the pen work here. What's the chance of accepting H0 when H0 is false? We are told that H0 is false because P has indeed decreased. It is indeed less than 30%. It's now 20%. So our number line, we're accepting the null hypothesis for 5, 6, 7, 8, and we're rejecting the null, therefore saying there's evidence of H1 for anything less than. Anything more than, we're accepting. So yeah, reject for anything less than or equal to 4. That's the critical region. And that would be us correctly rejecting H0 when H0 true. So if you do less than 4 straight away, you get the power straight away, and that's where the calculator's paused. But let's say we've gone through the motions of working out a type 2, because that's what we've been trained to do. Work out type 2 first, because we might be asked for type 2. The acceptance region is actually 5 or more. So on your BCD now, put 5 as the lower. Let's work out our type 2 error. Put 5 as the lower. 25 is the sample size, so that will be your upper. But make sure you change your proportion to 20% now instead of 30. Do you get a type 2 error, which is relatively large, of 0.579? Okay? And because we forgot to read the question, we weren't actually asked to do a type 2 error, but luckily we have, because power, which is rejecting H0 when H0 false, is the opposite of accepting H0 when H0 false. So it's 1 minus our type 2, and 1 minus 0.579 is that 0.421, which you can generate from 0 to 4 in your BCD straight away, if you're happy with the definition of power being rejecting H0 when H0 false. Okay? So this is our first example of binomial. It's all to do with critical regions and where the number line changes and where that decision changes. The difficulty, yet again, with a type 2 is one of your parameters changes. In a normal, your mean changes. In your binomial, your proportion changes. And the difficulty there is just making sure you're happy with your definition. It's quite definition heavy. So if you need to, pause this video, re-watch it until you're happy with this example before looking at example 2. Okay, our second example. It looks a bit more wordy, looks more like an exam style question. I've already highlighted that, we have already highlighted that it's a two-tailed test, but let's talk through why that's the case. Because it says that it claims that it is 95% of adults who have the flu jab who do not catch flu during the next 6 months, we're going to test that hypothesis. It doesn't specify whether somebody believes it's higher, lower, it doesn't specify. So naturally, the alternative is not. That's why it's a two-tailed test. Be careful, 5% level. So the actual genuine area we're going to compare against, the actual probability we're going to compare against is 2.5% left and 2.5% right in our number lines. Okay, so set up the model. Just going to fill in a couple. I will go through the question in a little bit more detail than's actually being asked. So therefore, we're practicing critical region definitions as well as type 1 for a binomial, because like I said before, type 1 for a binomial is slightly trickier, as well as type 2, even though this question asks for power. We could have worked out power directly, but I'll go through the process of working out type 2, because it's actually easier for a binomial, because we have lowers and uppers, rather than the power being the rejection regions either side of this value, to the left of this value, to the right of this value. Okay, set up your model. You've got your sample size and your proportion. Let's assume that proportion is true for now to construct our critical region. But we're actually being asked for two questions. We're being asked to carry out a test using the sample. Be careful, if you're going to use 10, you'll end up with a small probability or a big probability depending which way you test. If 10 did catch the flu, then 110, which is 120 minus 10, did not. So that's a good starting point. The difficulty with binomial two-tailed questions is we don't know where to test. Should I be testing for less than or equal to 110? Should I be testing for more than or equal to 110? If you work out the mean of your distribution, your expectation, which is n times p, for this question 120 times 0.95, which comes out 114, that's a lovely starting point. Anything smaller than 114, we're testing left. Anything bigger than 114, we're testing right. So we're testing left for 110 initially. So if you put 0 as your lower, 110 as your upper, oh, what a shame, that p-value is not quite small enough. Make sure you compare it against 2.5%. Yes, it's bigger than 5%, but we need to compare it to 2.5 because it's two-tailed 5%. So we're going to accept H0. There is no significant evidence to suggest that the proportion of those who do not catch the flu during the next 6 months after having the jab is not 95%. We are accepting H0 because there is no significant evidence of the alternative being H1. And like I said before, it didn't specify that it's not 95. We had to make that assumption. So we've had to write H1 in context ourselves for this conclusion. Okay, so we've done the first part of this question. Test and calculate. That's the second part now. Power. Well, to work out the power, we need to work out the regions, whether it's the acceptance region for type 2 or the rejection region for for power. And then, of course, we'll do those probability calculations with this new change, this proportion of 98%. So where is the cutoff? Where do we finally get less than 0.2025? So it would make sense to then try 109. If you're unsure where to start, you could always use inverse binomial, but thankfully here they gave us a starting point of 110, even though they didn't explicitly write 110. So 109 upper is smaller than 5%, however, and you can see how some students make this mistake, we're not comparing against 5%. It's a two-tailed 5%, so actually That's bigger than 2.5%. Let's keep going. Hopefully 108 now. Is that small enough? So 180 is your upper, 0 still is your lower. Sample size 120 and proportion 0.95. 0.0173. So that is us finally finding our first reject. And you've got to have the last accept and the first reject. Or if you found the last reject, you've got to keep going to find the first accept. I'm going to underline the probability as well as the region. Let's do the other side of 114 now. Let's try 117. Sorry, let's try 118. If you try 117 as your lower, 120 as your upper, 120 is your sample size 0.95, you end up with a probability bigger than 0.025. So let's go further away from the mean. Let's go 118 now. I get a probability that is bigger than 5%, bigger than 2.5%. So we're accepting for 118, which, if I'm being honest, the reason why I started at 118 is because I did an inverse binomial. Okay, so it wasn't small enough. Let's go to 119, further away from that 114. Yes, we found it. You may not find two consecutive numbers where your decision is different straight away. The inverse binomial helps, but trial and error also works, starting from your mean outwards, and it might take a while. What you write down for the examiner, you have to write down a bare minimum of the last accept and the first reject. So I've finally found where it changes. 118 still accept, 119 or more, because it's to the right of 114, creates a p-value of 0.0155, finally rejecting. So we found our critical region, or critical regions. (108) or less. 109 we were accepting still. 118 we were accepting still. 119 we were finally rejecting again. So 119 or more. So that's also critical. So I know the question didn't ask for it, but the actual type 1 for this question is both of those probabilities because we have two critical regions. So if we add them together, we have a total probability less than 5%. 0.328. Okay, type 2 error time. So the acceptance region. Just a reminder of our definition. Type 2 is accepting H0 when it's false. Are we told it's false? Of course we are. We're told the proportion changed to 98%. Now the acceptance region is between those two values, 109 and inclusive to 118. So in your BCD, 109 we decided was an acceptance, 108 was critical, so 109 to 118. So 109 is your lower, 118 is your upper. Yes, your sample size is still 120, but because we're now onto two type 2 errors and power, that proportion has changed to 98%. Did you get a relatively large type 2 error? It's changed from 95 to 98, so yes, type 2 error is still quite large. That is our type 2. That was our probability associated with the acceptance region for the old proportion, using the new proportion as our parameter, i.e. H0 was false. The power of the test is when that proportion has changed, what's the chances we're going to correctly reject? And that's the opposite of our type 1, our type 2. So if you work out your type 2, you can simply take your type 2 away from 1. The power for this question is only 30.5%, 0.305. Couple of ways you could improve power. To increase your power, you've got to decrease your type 2. So how can we decrease the type 2? You can increase your type 1, or you can increase your sample size. Hopefully you found this video useful. Make sure you look at the other two videos for normal. And as always, if you have any questions, feel free to ask your tutor or myself. And yeah, best of luck in your studies. Cheers. Thanks. Catch you in the next one.